Hello everyone, and in this video we're going to be making our first real program in NASM assembly. So we're going to be writing hello world. So we're going to write it regularly as maybe a NASM developer would, and then we're going to write it as though we're writing shellcode, and then we're going to actually look at the actual machine code, the opcodes. So the first thing I wanted to show you is this handy resource here. If you remember last video, we used one syscall for exit, and here is a table of all the x86_64 syscalls. So as you can see here, the first column is the number that the syscall is referred to with. So sys_write is always the number 1 into RAX, and then the first argument it needs is the file descriptor, and then a pointer, and then the size, blah blah blah. And you can see there's a lot of syscalls, so we're very lucky that people have documented them for us like this. And the one we used last time was exit. If you remember, we moved 60 into RAX, and then we moved the status code into RDI, which was 0. So I just wanted to show you guys, there's a lot of syscalls. We'll be using some of them, and others you can maybe figure out how to use on your own when you're writing some NASM programs yourself. But now we're gonna dive into today's program. So we're back in Ubuntu, and we have another program that I've written, and this is just gonna be your simple hello world program. You always make a hello world whenever you're learning a new language. So the first 2 lines, I'm sure you already know what those are. Covered them in my last video. And this time, we're going to be setting up for the right syscall. So the first thing we're going to do is move the number 1, the immediate value 1, into RAX, which RAX again always holds the number of the syscall you want to perform. And if we look at this table, you can see that sys_write is the number 1. Next, you move the file descriptor for std out into RDI, which is 1. And looking at the documentation, into RDI goes the file descriptor. And if you were to check some header files or just look it up, you could find out that 1 was standard output. Now into RSI, we need to put the address of our string. So down here in the data section, I've defined a series of bytes, hello world, and we're moving just the address. Remember, we're not dereferencing it into RSI. Then we're going to move the length of our string, which is 11. If you just count HELLO world, etc., that goes into RDX, as you can see here. And then we make our syscall. So that'll print our string, and then we want to exit the program. And the way we do that is just as last time. We move 60, which is the syscall for exit, into RAX. Then we move the status code into RDI, which is 0, and then we make our syscall. And a quick word about AT&T syntax. If you were to write AT&T syntax, you have to specify a length, so move long, and then you do the value. The source comes first, and then the destination. So it looks like that, and you can see it's very messy. It's not as clean as Intel by any means. So you can see how that would get a little messy. So we're just going to do it the regular way with Intel. Okay, no typos anywhere, so we're gonna exit, assemble, and link. TAC F is for format. We create an object file, then we link it. So now we have our executable, and if we run it, it prints hello world. Okay. So that was very nice. And now, say we wanted to make, for whatever reason, you wanted to make hello world shellcode. So you were gonna inject opcodes into a program, and you wanted the program to spit out hello world. I don't know why you would, but let's say you did. If you wanted to get the opcodes, you would use objump TAC-M Intel for the Intel syntax, and then the binary. You could also use the object file. And you can see our assembly here. It's exactly what we did. I'm not sure why. I think it just changes RX to EX because we're not using that much space, but I'm not positive. But if you see, we have a bunch of null bytes. When you're writing shellcode, you can't have any null bytes most of the time because, as I said in my brain pan video, they truncate data and they symbol the end of string and all that stuff that we don't want. So what we're going to do is we're going to rewrite our hello world program, except we're going to get rid of the null bytes. So if we we copy our original source code into a new file, and we're gonna just change some stuff. So the first thing we want to do is to clear our registers. And then what we want to do is, instead of move RAX1, we can just do inc RAX. And there's multiple ways you could do this to put 1 into RAX. You could do add RAX1, but let's show inc RAX, which is just increment by 1. And this is the fun part because you can get creative with how you write shellcode. We can do this method, add 1 into RDI for the file descriptor, just as long as we're not doing move RDI something, because that would produce nulls. We're gonna move our string address into RSI, and we're going to add 11 to RDX. Then we're going to clear. Actually, it's shorter if I do this up here. Then we can actually do move AL60, so we're only filling up the lower 8 bits of the register. So that would produce no nulls. And then for the status code, we can just clear RDI to put 0 into it. The only line I'm not sure about is this one right here. This might produce nulls, we'll see. Let's check for nulls. And we do have nulls, but we got rid of a lot of them compared to the other one. So we just have to figure out how to get rid of these nulls. And I figured a good way to get rid of them would be to show you the, it's in the shellcoder's handbook. It's called the jump call pop technique. So what you do is you basically utilize the way call works and the way pop works in order to move your string address into RSI without any nulls. So I've written a new program. And we're starting off the same. You should know these first 2 lines. And then when we enter into start, the first thing we're going to do is an unconditional jump. So an unconditional jump means you jump to the next to that subroutine no matter what. So if we follow our program execution, we go to the label call underscore shellcode, and if you look at call underscore shellcode, it's going to call another subroutine, which is execute shellcode, but the next quote unquote instruction is defining a string. So what's going to happen is, remember, when we use a call instruction, it will push the address of the next instruction, in this case our string, onto the stack. So what we're doing is, when we jump to this subroutine, we're going to push the address of string onto the stack. And that's how, normally this would be the return address, but in this case, it's just going to be the address of our string as well. So we go to execute shellcode, and we pop RSI. And that's going to take the last thing that was pushed, which is the address of our string, and put it into RSI. So that's how we can get rid of the nulls. We're going to clear RAX. We're going to move the syscall for write into RAX. We're going to move one RAX's value, which is 1, into RDI. So that's standard output. We're going to move the length of our string into RTX, but we're going to do it without nulls. Then we're going to make our syscall, and then the rest of the code should be pretty familiar. We're going to exit. So let's check on this program, see if there are any nulls here. Let's check. And you can see we don't have any null bytes, which means that this would be valid shellcode to use, assuming there are no bad characters. So now let's link this. And execute. And you can see it just does what the other one did and prints hello world. So now let's step through this in GDB so that we can really understand it. Okay, so now we're going to step through our program with GDB and actually understand how it works. So disassembly flavored Intel, breakpoint at start, lay out the assembly, lay out the registers. And now we're at our first instruction. We're going to jump to the subroutine call shellcode. Now we're going to call execute shellcode and push the address of our string onto the stack. And now if we examine the stack, we should see the address there. Yep. There it is. Moving on. The next thing we're going to do is we're going to move this address into RSI. So now we successfully put the address of the string into RSI, which we need for the write syscall. We're going to clear RAX. We're going to move 1, which is the syscall number for write, into RAX. You can see RAX changed. We're going to move 1 into RDI for standard output. You can see RDI now has 1. Now we're going to add 11 into RDX, which is the length of our string. You can see RDX now is 11. We're going to make a syscall for write, and that would be where it prints hello world. We're going to clear RAX. We're going to put 60 into RAX for the exit syscall. We're going to XOR RDI with itself to put 0 inside of it so that it will now be the status code 0. You can see RDI zeroed out, and now we're going to exit. Alright. So I hope you guys enjoyed that. That's the jump call pop technique. You can also implement it with execv and bin sh. When I was doing it, I had trouble something with the text section and not being executable or something like that, so I can't do a video on that, but there's plenty of documentation about that. It's in Shellcoder's handbook. Basically, it just uses the same principle, except the thing you push on the stack isn't the address of the string. You push bin/sh on the stack, and what you do is you push 0 onto the stack as the terminator, then you push bin sh, and then you're basically using jump call pop to set up the execv syscall, which we will probably use at some point. But that's kind of what you need to think about when you're writing shellcode, is how do I remove null bytes? How do I make things more efficient? In little tricks like storing EAX with itself instead of RAX. You can save opcodes. And little tricks like we did increment RAX in the other program. We did add RAX here. So lots of different methods. You can develop your own, I guess, style. And in the next video, which will probably be coming very soon, I'm going to show you this kind of cool program I wrote for some more creative shellcode. Like most shellcode you see is either execv bin sh, or a lot of people write exit shellcode just when they're starting to learn. But I had a cool idea, so I made a NASM program, and I'll hopefully show it to you guys this afternoon. Until then, I'll see you guys later.